Let us start our session. First speaker is A.Anokhina. 15 minutes in total, but 12 minutes for talking.
Good afternoon. I would like to present to you the possibility of the NEWSdm emulsion experiment to search for the cosmically boosted dark matter. NEWSdm experiment is the nuclear Martian experiment for WIMP search.
Please use the closer.
With a directional measurement carried out in Gran Sasso laboratory in Italy, and the main goal of this experiment is detecting the direction of nuclear recoil from WIMP elastic scattering. WIMP weakly interacted massive particles, hypothetic particles, for dark matter models. The target of the NEWSdm experiment is the nanometric emulsion films. The plastic base with emulsion with 20-40 nanometer grains developed in the Nagoya University in Japan. And this emulsion acting both as a target and as a tracking detector in the NEWSdm experiment. There are many other experiments for WIMP search carried out in the last 20 years. The scheme of such experiments you can see on this slide. Our Earth, when moving in the galaxy, meet the wind of cold dark matter. Cold dark matter particles interact with atoms with nuclei and electrons in the target of the detector. Nuclei and electron take the energy and can be detected. Acquire energy by elastic scattering and can be detected. In our experiment, the detector is the nuclear emulsion. Nuclear emulsion is a gelatin gel, consists of carbon, oxygen, nitrogen, and hydrogen atoms, and argentum brom crystals for visualization charge particle tracks. To register WIMP, weakly interacted massive particles, it was supposed to place the emulsion detector on the special platform currently oriented on to the Cygnus constellation for the all time of exposure. On this slide, you can see many other experiments devoted to search such WIMP particles as supersymmetric extension of standard model in mass ranges from 1 GeV to 1 TeV. And you can see for some mass ranges, The constraints on the cross-section DM nucleon interaction is close to neutrino flow, and and we know that not dark matter particles in this mass range from 1 GeV to 1 TeV not registered on the last step. We estimate the sensitivity of our emulsion of 30 kilogram of our emulsion for such WIMP called WIMP wind. And on this slide, you can see the track length distributions for carbon and hydrogen recoils, and angular distributions for track for these recoil tracks in the emulsion with density of 3.44 grams centimeter. The zero direction is corresponds to the Cygnus constellation, and when we if we put the threshold on the track length, after applying the threshold limit on the track length, it becomes clear that only about one event associated with the elastic WIMP scattering in our emulsion, we can expect it in one. Now we consider cosmic ray boosted dark matter. The idea was put forward a few years ago, and now now we can explain how many recoil events can be expected in 10 kilogram of our emulsion during 1 year of exposure, and is it possible to expect an excess of the signal from the galaxy center direction? On this slide, you can see the galactic cosmic ray map obtained by Galprop code, and this is galactic dark matter map obtained by Navarro-Franco-White profile. And you can see in the vicinity of the galaxy center, we can take excess of boosted dark matter by interaction with high-energy cosmic rays. And there are our first results. There is the sensitivity curves for the NEWSdm detector for the mass ranges from 1 keV to 1 GeV. In the range of cross-section DM proton and cosmology and other experiment constraints. And and the second our second question: are the tracks of the recoil nuclei directed to the source of dark matter particles? Now we consider the primary DM particles, the point of recoil production, and the track production in the emulsion. And now we compare the number of track in the angle ranges from 0 to 13 and for 16 to 19. And our answer, the directionality effect is 3.5 times more tracks from CNO and hydrogen recoiled nuclei in the emulsion can be expected from dark matter particles with masses from 1 keV to 1 MeV. Our next step is the two-component dark matter model for NEWSdm emulsion experiment. And this is the steps of our next modeling. The left diagram is the production of boosted dark matter B particles through the annihilation more heavy first component dark matter in a galactic center. And these three diagrams is the scattering of boosting second DM component in the emulsion target. This is the scattering on the electrons, and this is the scattering on the nuclei protons. And the energy of this boosting dark matter may be very high, and the process of deep and elastic scattering in the emulsion will be considered. Thank you for your attention.
We have time for questions. Okay. We have time for questions. No. First, Evgeny.
Yes, with the limit reported, for example, yesterday in for Panda X experiment, do you expect to see any events? Because we know that there is no events in like 1 ton year data. There is no dark matter events.
No, we have no data now. It is only...
Yeah, but you still need have an expectation, right?
I know, but Panda is underground experiment.
Right.
Our goal is the surface experiment to develop. There are many distortions of the dark matter spectra, and this is our attenuation processes in the.
So do you mean SIMP and etc.? So not WIMP, but SIMP search. The so-called strong interacting massive particles, or what?
This model I now not analyzed for our DM,
Okay.
DM experiment.
Okay, thank you.
Short question and short answer.
Do you have the Lagrangian model to derive diagrams on the last?
Yes, I think it will be a model with dark photons and dark photon interactions.
Extension of the standard model?
Yes.
Okay.
With dark photons and dark particles, dark interaction with
Dark massive photon, yeah?
dark massive photons, yes.
It's not photon, of course.
Yeah, probably also I have a short question about usage of Navarro-Frank-White model for your experiment, because the solar system is located near spiral arm. So, but it's in general, Navarro-Frank-White is like general approach is good, but It's probably we have some excess of mass, including dark matter, because it's spiral arm.
I agree with you, but it's only
Just illustration.
illustration.
Ah, okay.
This-
Okay, let us thank speaker again.
really-
Thank you very much. Next speaker is Professor Zhang. Okay, student. Okay, future professor.
I hope so. Anyway, it's an honor to be here to give a brief
Speak
presentation.
closer to
Oh, yeah,
microphone.
actually. And I'm gonna introduce our newest result on the dark matter electron interaction detection via the high purity germanium detectors from the CDEX experiment. I'm Zhang Zhenyu from CDEX group, Tsinghua University. There have already been a variety of direct detection experiments, and there are mainly two types of experiments. One type is that experiments using the solid state detectors, and the other type is experiments using the liquid scintillators like xenon and Panda X. There's some images of the experiments. And previously, most of this kind of experiments are they mostly focus on the dark matter nuclei interactions. Not until recently, there is a dark matter electron interaction paradigm has drawn much of the attention of the physics room. And so why this dark matter electron interaction? Well, for dark matter nuclei, it is there is a certain level, a certain lower dark matter reach that below which you can hardly get any permeability due to the mass mismatch between the dark matter particle and the nuclei. Because if the dark matter particle is too the mass of the dark matter particle is too small, and it can hardly deposit enough energy to induce an observable signal on the detector. But this is not a problem for electrons because they are much more lighter, and they can extract energy from light dark matter particles more efficiently. And as a result, we can have a great permeabilities for light dark matter particles. And currently, the lowest dark matter reach of the dark matter nuclei experiments is at the GeV level. However, for the dark matter electron interactions, the mass reach has reached to MeV level, and for some accelerated dark matter analysis, the mass reach has already reached PV level. There's also some other interactions that are being studied, but this is not today's topic, so we just move on. So if we want to utilize this dark matter electron interaction paradigm, so what do we do? What do we need? The first thing we need is predicted rate in detectors, because we have this and we can compare it with the experimental data. So how do we do this calculation? Well, this is how we do the calculation, and the most important part is the form factor here, that involves the wave functions of the final and the initial states of the electronic states in the atom. This calculation for noble gas target is relatively simple, because atoms for noble gases are considered isolated. So the electronic states in the noble gas target are already well tabulated. So what you need to do is just to look them up and calculate the predicted rate. But for crystal targets, specifically for germanium and silicon targets, like our high purity germanium detectors, the crystal is a many-body system, and the electronic states, they are strongly turbulated by the crystal environment. So this calculation for crystal targets is very complicated. So how exactly we can do this calculation? Well, there have been many efforts. There was some semi-analytic approximations that incorporate the structures by taking the density of states into account. And there is this energy loss function method, and there is this density function theory. And this is a method that calculates the valence and conduction band structures and the wave functions in it. And this is currently the routine method when it comes to the dark matter-electron interaction calculation. And this method is in depth in the QDark package. And with this package, there have been very good results derived from all the kinds of experiments, especially with those experiments with very low threshold. But this is still a problem for our high purity germanium detectors, because the predicted spectrum calculated by QDark packages only extend up to about 50 eV, which is okay for those experiments with a very low threshold. But our high purity germanium detectors have a typical threshold of about 160 eV, and this means that we cannot get a predicted rate above our threshold. It means we can see nothing. With nothing, we can do no analysis. So how do we bypass this barricade? Well, we can, because our threshold is that we can currently we can hardly do anything about it. But luckily, there have been some new advancements in this topic, and there's a new package called XCDM that enable us to do this analysis. So what is XCDM? XCDM is a new technique that incorporates both DFT and semi-analytic methods. So what does it do? The major character of this package is that it categorizes all the electronic states in the crystal environment into 4 categories. That is free, core, and valence and conduction. For free states, that is all the states above 60 eV. The electrons are considered as free electrons, and they are modeled as plane waves. And for those states that are closer to the core, and they are modeled with semi-analytic method. And for valence conduction, then they are modeled with DFT method, but there's a all electron reconstruction used here to retrieve the high momentum components of the wave functions. So compared with QDark, all right, yeah, XCDM has a more complete model of the all the electronic grids. So as a result, it has a more complete spectrum predicted, and it can reach up to KV, which is considerably larger than our energy threshold, enable us to do some analysis. And here's the result we can see. So in the low energy region, the QDark result in orange lines are accord with the result from XCDM. And this means that for some experiments with very low threshold, if you use QDark or if you use XCDM, the result will only have some minor difference. But for us, this is the difference of like from 0 to 1. It's so it will be some major improvement for us. And with the predicted rate, we can finally get the rate predicted spectrums actually seen by the detector that is convolved with the energy resolution. And here's the energy resolution spectrum with energy resolution in the both heavy mediator scenario and light mediator scenario. And right, there's something I just skipped it. And this is the data from CDEX. The data set is from the CDEX experiment, and it's from the CDEX-B germanium 1 detector. And the total exposure is about 205.4 kilogram dot day. And the raw data goes through the treatment of pedestral noise cut, physics, event selection, and both bulk surface discrimination. And finally, non-radioactive peaks are subtracted according to the KX intensities in the high energy region. The final threshold is 160 EV, where the signal efficiency is 4.5%, and the resolution is determined by this equation. And with the experimental data and the predicted spectrum seen by the detector, we can now finally do an analysis. And the energy range is from 0 to 2 keV, and of course it's not 0 to 2. And the beam width is 100 eV, and we use the chi-square method, and we adopted one side upper limit of 90% confidence level. And here's our result. And this is the first chi result from the high purity germanium detectors working in the temperature of liquid nitrogen. And as you can see in this figure, in heavy mediator scenario, our result proves to be the most stringent result among all the other solid state detectors based on the experiment in the mass range of about larger than 100 mem. And this result is published on PIR last year. And to sum everything up, I'll just wrap it up. This result reveals the vast potential of such technical route, that is probing dark matter electron interaction with high purity germanium detectors. And here's a little question you may ask, is that as we can see in the spectrum predictive spectrum calculated by CDEM a couple of pages ago, the expected signal drops drastically as energy grows. But our high purity germanium detectors has energy threshold that is not that ideal. So how do we get this strong probing ability, this strong sensitivity? Well, the answer is that the superior ultra low radiation environment in CDPL in the Jinping underground laboratory, it compensates the loss of sensitivity due to our high threshold. And for our next steps, the CX50 experiment, which used in an array of 51 kilogram high-purity germanium detectors, where the radioactive background will be further reduced to about 0.01 count per kV per kilogram per day in the sub-kV region, which is 200 times lower than our current background level. We anticipate that we can get an improvement up to 3 orders of magnitude. So this is it. Attention. Yeah.
We have time for a couple of questions. Okay, Evgeny.
Yeah.
Evgeny, please sit closer.
So my question is, so you considered energy of that up to 200 electron volts electron can be produced, right? About 200, so maximum energy of electrons is about 200 electron volts, right? Yeah, so this energy is only enough for excitation of m electrons. So all your scattering will happen on free electrons. And number of such electrons in germanium is rather small. So do you take this into account?
Sorry, you mean?
You know, the energy is small. The energy of scattering energy is small, and almost all electrons in germanium, they are binding in atoms. So you don't have enough energy to take electrons from atom.
Yeah.
So scattering can happen only on free electrons or valent electrons.
So you mean? Sorry. You mean somewhere on this figure? This is predictive spectrum.
Yeah. So predictive spectrum, you number of electrons in the germanium.
Yeah.
What is this number? Number of so when you calculate that expected spectrum, you have to take dark matter flux,
yeah,
and then you consider number of electrons it can be scattered in germanium. So this number is what this number?
I see. Yeah, I know. There is something I skipped. You remember? Here. This is. I mean, if the energy is large enough, I mean the electrons is enough. So it's okay. We apply the energy threshold to it, right? Yeah, but for like you said, if the energy is too low, there will be some only like about 10 eV. Just for an example, like 10 eV deposit on the detector, so there might be just only like 5 or 8 electrons excited, and you mean you cannot see them, right?
No. Not my question. Not that you cannot see it, but you just don't have electrons to be scattered off. So almost all electrons in germanium, they are binded in atoms. And you don't have enough energy to excite them.
Well, this is not up to me. This is what the package tells me. So.
Okay.
I think, yeah. But I think
Thank you.
Because, like I said before, in the low energy region, the result accords with the predoc, which is publicly accepted, like a common method. So I think this method should be fine because if the energy is too huge, the count rate is actually very low compared to the low energy region. So I think it should be fine. I hope.
So, questions from Zoom?
Sorry.
Your floor is still yours.
There's no question.
No question. But remember, very soon you will be real professor. It's remember my prediction. Okay.
I hope so.
Next speaker is Dr. S.Chashin. He is here or not? Okay.
Right. Good evening. Today I will present the current status of the direct search for low mass dark matter with dark side 50. First of all, a couple of words about the dark side 50 experiment. The main part of the detector is the dual phase argon time projection chamber, which is filled with 50 kilograms of highly purified liquid argon with a small gas pocket on the top. The chamber is surrounded by the field cage rings, which create the needed configuration of the electric field. And also on the top and the bottom of the chamber, there are arrays of photomultiplier tubes, 19 PMTs in each. The chamber is surrounded by the liquid scintillator Vito, which is filled with 30 tons of boron-loaded liquid organic scintillator. And the Vito is surrounded by water Cherenkov Vito, which is filled with 1,000 tons of ultra-pure water. The detector is located in the underground hall in the National Laboratory Grand Sasso in Italy. Right, so when the recoil energy in the dual phase argon time projection chamber, the recoil energy of the target particle after the interaction is can be detected via scintillation photons, which form scintillation signals 1, and ionization electrons, which are extracted by the electric field in the gaseous phase. There happens electroluminescence, and it forms the ionization signal S2. So both the amplitude of both signals S1 and S2 provides colorimetry, and also the both signals provide particle identification via pulse shape discrimination. The drift time between S1 and S2 also provides Z-coordinate reconstruction. In case of the low energy event, the S1 signal becomes unavailable because amplification in gaseous argon lets us detect signals with much higher efficiency. So the detector has much lower energy threshold for S2 signals. But in this case, pulse shape discrimination and drift time are not available. So for detection channels, first of all, there is elastic scattering in forms of either nuclear recoil and or electric recoil. In case of nuclear recoil, due to the high mass of the nucleus, the search sensitivity is higher in the high mass range of dark matter, up from about 5 giga-electron volts. On the other hand, for electron recoil, the search is more sensitive in the low mass range, between about 30 mega-electron volts to 5 giga-electron volts. And for the inelastic scattering, we have the atomic effects, mainly the Migdal effect and the Bremsstrahlung emission of the recoiling nucleus. Both of these effects are based on the assumption that electron shell follows the recoiling nucleus with delay. And both these effects are also more sensitive in the low mass range of dark matter. So here you can see the dark-side 50 dataset. It consists of more than 650 live days of underground airgun data, or 12 ton days of exposure. During the 26 months period in which the data was taken, detector showed this instability, the internal parameters and the amplitudes of S1 and S2 signals were quite stable. On the data, there were some quality cuts applied, which can be seen on this slide. And after the cuts, the signal efficiency in the region of interest is more than 95%. The region of interest for low energy analysis is between 4 and 170 ionization electrons. Of course, after the cuts, the data should be compared with the background model, which for dark matter, which for dark side 50 consists, which for dark side 50 provided by the Monte Carlo modeling, and is based on a series of calibration campaigns. Internal background consists of argon 39 and krypton 85. And external background consists of impurities in photomultiplier tubes and cryostat materials. Also, there is the background of spurious electrons that follow the large S2 pulses, but the origin of this is currently unknown. So, for standard low mass SWIP search, both S1 and S2 signals were taken into analysis. And the search was taken for nuclear recoils with pulse shape discrimination. To improve sensitivity in this region, there was extended exposure, improved dot selection criteria, more accurate detector calibration, and better background modeling. And the general results can be seen here in red. As you can see, this approach allowed us to set the most stringent exclusion limit of all experiments in the mass range between 1.2 and 3.6 GeV. For S2 only WIMP search, as I said before, using only S2 signal in analysis allows us to increase sensitivity for low energy interactions. But pulse shape discrimination and Z-coordinate reconstruction becomes unavailable. As seen on the slide, on this plot in blue, S2 signals amplified in gaseous ergon allow us to identify even the single ionization electron. For dark matter electron scattering, we have different dark matter candidates, such as, first of all, Fermi non-scalar boson light dark matter, or LDM for short, which is the main dark matter candidate. And they interact via vector mediator and provide ionization. Also, there are pseudoscalar dark matter, also called axion-like particles, or vector boson dark matter, dark photons. And they can be absorbed by ergon shell electron and provide monoenergetic signal in the particle rest mass. Also, there are sterile neutrinos that can inelastically scatter bound electrons and produce ionization. The results for LDM are shown here, and on the left there are the approximation of heavy mediator, and on the right approximation of light mediator. In both of these approximations, there are the most stringent exclusion limits obtained for the heavy mediator between 16 and 56 mega-electron volts, and above 80 mega-electron volts for light mediator. For different more exotic dark matter candidates, the exclusion limit was calculated for model parameters: axion electron coupling strength, dark photon kinetic mixing strength, and sterile neutrino mixing angle. So in the last, the atomic effects. So the delayed movement of the electron shells after the recoiling nucleus can result in the polarization of the atom, which can lead to ionization and photon emission. This is called the Migdal effect. Also, accelerated movement of the recoiling nucleus in the electric field of its electron shells can be followed by Bremsstrahlung photon emission. But as can be seen on this slide, the rate of this effect is quite low, and for current exposure, this effect is negligible. So here are the differential ionization spectra calculated for different dark matter masses for Migdal effect. And for the results as shown in red, this approach allowed us to set the most stringent exclusion limit at, for dark matter nucleon interaction cross section between 40 mega-electron volts and 3.6 giga-electron volts. It should be noted that the limit is entirely driven by Migdal effect up to 0.5 giga-electron volts. And the limit in this mass region is not affected by choice of quench fluctuation model. And for the conclusion, we have the detectors with dual phase argon-10 projection chamber, such as dark side 50, are able to significantly increase the dark matter search capabilities in low mass region. Also, the advanced analysis methods can furthermore increase sensitivity of low mass dark matter search, and everything is limited by exposure, so increasing of exposure is crucial for low mass dark matter search, and it can be reached by the next stages of the dark side program, dark side low mass and dark side 20K experiments. Thank you.
Thank you very much. We have only one question, if there is one. No? No? Oh, okay. No. Oh, no. No, only that. Please.
Neutron background for the dark side.
Neutron background is mitigated by liquid organic scintillator vetoes, since there are boron infusion and neutrons recombinate with them. And the water Cherenkov veto also help to capture neutrons from outside.
Okay. We have to go ahead. Let us thank speaker. And next speaker from internet
Hello, can you hear me?
Yes, we hear. Demonstration of your screen.
Your presentation.
Yes, just a second. I'm sharing the screen. Okay, I think that you can see it, right?
Excellent. Go ahead. 12 minutes.
Okay.
12 minutes for talk and 3 minutes for questions. Please go ahead.
Okay, I try to be fast. Okay, so good afternoon, everyone. And yeah, I will show you some recent results from searches for invisible new particles at Belle II. This is just a brief introduction on dark matter. So as you know, it is one of the most compelling phenomena in support for physics beyond the standard model. And we know that it exists and we observe its gravitational interaction. However, we don't know anything about its nature. So we design different kind of experiment to try to search for dark matter. And you already heard a lot about direct searches, and now the focus of my talk is on Belle II, which is an experimental collider. So in this kind of experiment, if dark matter is weakly coupled to standard model particles, then it can be produced in standard model particle annihilations in the accelerators, involving LiDAR sector mediators too. So what are LiDAR sectors? So basically, as I said, currently there is still no evidence of dark matter at the L2 scale in experiments, and this motivates the introduction for LiDAR matter with a mass of the order of MeV or GeV that need like dark sector mediators that are involved in the interaction between standard model and dark matter particles. And in experiment, we can have several signatures that are briefly summarized on this plot here. And the description of the interaction is done through some interaction portals that depend on the kind of the mediators, as shown here. And these extensions of the standard models are very interesting because they may solve the dark matter puzzle and also explain some of the long-standing anomalies observed, like the G-2 of the muon. So for what concerns the Belle II experiment at the Super KKB Collider, I will give you just a few information. And if you want more details, please refer to Pavel Pavlov's talk. So as you know, Super KKB is a new generation of B-factory, and it provides luminosity to the Belle II detector, which is a major upgrade of the Bell detector. And up to now, we collected 424 inverse femtobars of data, and currently we are not in data taking. We will resume data taking at the end of the year. So the main features of this kind of experiments are the well-known initial state condition and the clean environment. And we have also some dedicated low multiplicity triggers to suppress the high cross-section QED processes without killing the signal we are interested in, like, for example, dark sector signals. And to design these trigger lines is challenging because it requires to have a precise knowledge of the acceptance and efficiencies of the detector. An example is the single photon trigger, which is available in the full collected dataset at Belle II that makes the Belle II dataset unique. So all these features allows to have excellent reconstruction capabilities for low multiplicities and missing energy signatures. Okay, so that was my introduction. Now let me move to the main part of the talk. I want to start showing the result for the search for an invisible Z prime boson. This is introduced from by the mu minus L tau extension of the standard model, and it is a massive boson that couples only two leptons with mu and tau lepton numbers, or dark matter if a dark matter particle kinematically accessible exists. So it can decay in different ways in an invisible state like neutrinos or dark matter particles, or in a visible state like a muon or tau pair. This plot here shows the branching ratios of the Z primes into lepton. And of course, if there is a dark matter particle accessible, then the branching ratio of the Z prime into invisible will be 100%. For this analysis, at Belle II, we profit from the excellent capabilities for missing energy signatures, and we search for it through the process plus minus into mu plus minus plus missing energy. Here there is the Feynman diagram, where the Z prime is emitted as a final state radiation from one of the two muons in the final state, and we search for a narrow peak in the recoil mass of the two final state muons. The main background here is due to tau-tau events, and we suppressed this background with applying some neural network that are trained simultaneously on all Z prime mass hypotheses, and they are based on the Z prime property to be emitted as a final state radiation from one of the two muons. So basically, this is a different origin of the missing energy with respect to the main background, where, for example, for the tau-tau is due to neutrinos. There are some remaining background that you can see in this distribution of the recoil mass, and they are mu-mu events and e-mu events. And we perform a two-dimensional fit without finding basically any significant excess in 80 inverse femtobars of data. And the main result from this analysis is that we can exclude the region of the parameter that can explain the G-2 anomaly of the muon for a Z prime mass of from 800 MeV to 5 GeV in the full invisible case. A similar analysis is the one for the for the search for a mu-mu resonance in 4 muon final state. This is a new result showed at APS, I think last week. And here there is the diagram. So you can see that it's very similar, but here the resonance decays to 2 muons. So we have a 4-track final state with at least 3 identified as muons, and we require the 4-track invariant mass compatible with the collision energy and nothing else in the event. So the signal signature is a narrow peak in the opposite charge muon mass, And here we need to apply an aggressive suppression of the main standard model background, which is due to 4 muon final state from QED. And this suppression is still based on classifier that exploits the feature of this kinematic distribution in signal event, that is basically the presence of a resonance in both the candidate and recoil muon pairs. This is the distribution for the muon invariant mass, and we perform a fit scan to extract the signal. And also in this case, we didn't find any excess in 178 inverse phantom bars of data. Here, the interesting thing is that we obtain some competitive upper limits on the Z prime model, which is, as I said, competitive with the Babar and Belle results that have been obtained with much higher luminosity with respect to the one that we used for this analysis. And then we can also set some first upper limits for a muon field scalar model, so the scalar decouples million into muons from a dedicated search. And so this is the first limits for this model that you can see here on the plot on the right. Okay, another similar analysis is the search for a tau-tau resonance in mu total final state. So here we have a resonance decaying to tau. So we have also here a 4-track final state because we reconstruct only tau decaying to one charged particle. And we, in this case, signal events are expected to peak in the recoil mass distribution of the mu here in the final state. Also in this case, we applying background rejection to reduce event contamination with missing energy, not associated with signal signature. And we exploit some 8 classifiers trained on different regions of the recoil mass, based also in this case on the fact that the resonance is emitted as a final state radiation, and also that we have a tau-tau system in the final state. And then the signal is extracted to a fit to the recoil mass distribution. Here you can see the distribution with a fit, an example of the fit. And you can see that there is a large discrepancy between data and simulation, and this is due to some effects that are not correctly simulated, like the initial state radiation in the 4-lepton final state that contribute a lot in the low mass region, and some missing processes that contribute to background in the simulation here at higher masses. So we measure basically the background directly on data to minimize the impact of this.
Excuse me, Luigi, you
Yes,
have 5
yes.
minutes more for your presentation.
Okay.
5 minutes more.
I'll try to be fast. Yes, thank you. So not correctly simulated backgrounds. However, the background is smooth, so it doesn't mimic the signal. Here you can see the result. We didn't find any excess in 63 inverse phantom bars of data. And here the main results are that we can limit some models for the first time, so some world-leading limits, in particular for a leptophilic scalar model with mass higher than 6.5 GeV, that you can see in the plot here on the left, and for an axion-like particles decaying into tau. These are also in this case the world-leading limits. Now let's change a bit the kind of process. So this is the search for a long-lived spin-zero boson in B2S transitions. So this is a long-lived particle that can mix with the standard model X boson with mixing angle theta s, and it is natural long-lived particle for small values of theta s. And here, some high performance in long-lived particle vertex reconstruction are necessary. And we reconstruct 8 exclusive visible channels, particularly the long-lived particles that decays into 2 charged tracks that can be electron, muons, pions, or kaons. And the B-meson decay is reconstructed as a prompt decay of a kaon or a K-star plus opposite charge tracks that make a displaced vertex. Here there are different kind of backgrounds, the combinatorial from QQ bar, and the K-short, which is vetoed in the pi invariant mass, and some additional peaking backgrounds that are suppressed with either selection on displaced vertices. The signal is extracted through fit to the long-lived particle reduced mass, separately for each channel and lifetime. Here you can see an example of the distribution. Here this basically the definition of the reduced mass, and this is an example for the long-lived particles decaying to pions. Also in this case, we didn't observe any excess in 189 inverse phantom bars of data, but we can set some first model independent limits at 95% confidence level on the product of the branching ratio of to Ks and the long-lived particle decaying to charge tracks. here on the right, you have the results for each channel and lifetime, and while here there is the interpretation as a dark scalar. So basically the exclusion of the region of parameters, theta s, and the mass of this dark scalar. So this is the last analysis I want to talk about. So this is, as you know, the charge lepton flavor violation is allowed in various standard model extensions, but it has never been observed. And there are different theoretical models introducing some alpha bosons that mediate the lepton flavor violation processes in tau decays. We search for these in tau events, and we separate a tag side and a signal side, and then tag side is reconstructed using 3 charged hadrons plus neutrinos. The presence of neutrinos does not allow to define the reference frame in which the tau signal is at rest. So we introduce an approximate reference frame, and we search for a peak in the normalized energy spectrum of the lepton, which is the distribution here, where you can see that in this reference frame for the background is quite smooth, and the background is the irreducible standard model tau to lepton nu, while the signal appears as a bump. So basically we search for this bump, and we didn't observe any sex in 63 femtobars of data, but we can set some world leading upper limits on the ratio of the branching ratio of the tau to lepton alpha over the branching ratio of the tau to lepton nu. Here you have the results for the electron channel and from the muon channel. Okay, so this leads me to my summary and conclusions. So I tried to show you how Belle II has a unique sensitivity to LiDAR sector and progressively will lead its exploration at luminosity frontier, providing some complementary results to higher energy colliders and beam dump experiment. And we already published some world leading results with partial data set, as you observed, so lower than the collected 424 femtobars. So updates for this analysis, new results are coming in the next year. Here I put a plot for an example for the Z prime to invisible to show you what we can do for different luminosities, in particular for the Belle II target integrated luminosity, which is 15 versatobar. Okay, this is the list of the analysis that I presented, so that's all for my presentation. So thank you so much for the attention.
Okay, thank you very much. We have still time for 1 or 2 short questions, if there are any. I do not see questions on internet. Please check it. Okay. Thank you very much. Grazie mille. Arrivederci.
Thank you. Thank you.
Next speaker is Dr. D'Yachenko. Is here or not? Who is D'Yachenko? I do not see.
Это все дистанционно.
Дистанционно, okay. Dr. D'Yachenko, are you ready?
1 minute.
Okay, you could share. Could you share your screen? Time is running. Okay, please full screen. We see your slides, but not full screen mode. Okay, go ahead.
Good evening. I am grateful to organizing committee for invitation and attention to me. My topic is on the issue of detection dark matter particle by D'Yachenko from Petersburg. Analyzing the spectra of ultra-high energy cosmic rays, confirmation of existence of new particles X17 and X38 boson with masses of 17 MeV and 38 MeV respectively has been found. These particles are not standard model particles. They were discovered early experiments accelerators. These experiments need independent confirmation, which was analyzed in our previous work within the framework of thermodynamic model. And the present work using the thermodynamic approach and independent confirmation
sorry,
of the
Alexander.
of these particles. Using the black body formula, it's possible to describe both the spectra of strange particles and spectra of new particles X17 and X38 with the formula for temperature already for a cold electromagnetic plasma when compared with experimental data for soft photon. Мы продемонстрировали с массами 17 МЭФ и 38 МЭФ спектра мягких фотонов, столкновениях протонов и ядер высоких энергий. Это было сделано в подтверждение.
Alexander, please speak English, because there are foreigners in the audience.
Ну, здесь все написано, в общем-то.
Please speak English.
They were discovered early experiments of atomic group and in collision of protons and high energy nucleon in CEIN boson X17 and in general Dubra boson X38. These new particles can be considered dark matter particles. Recall that the visible part of the mass of universe is only 5% in the universe. The obtained indication of the existence of these new particles need independent confirmation. These simple formulas can describe the spectra on PT for D meson and lambda diperons. And after that, we can describe the spectra of soft photons by the new particles X17 MeV and 38 MeV. On figure 1 shows the experimental spectrum of soft photons as well as calculation with the allowance for the X17 boson solid line and without it dashed line. The dotted line is the contribution from the X boson. It can be seen from the figure that without taking into account the contribution from the X17 boson, the calculation underestimates the experimental data and taking this contribution into account, reproduce them. The points from this work, the excess X17 boson predicted by atomic group. This our description. The X17 boson predicted by atomic group may manifested in spectra of soft photons. This was reported in Wong's papers as well as in our papers.
Excuse me, Alexander, do you hear me? You have 5 minutes more. Because in total, 12 minutes.
The mass of X bosons can be obtained from a tube model with combined QCD and QED model. The term NA determined by the field strength, and the second term is expressed in terms of back constant. And by this formula was obtained the mass of P0 meson and X17 boson and 38 boson. Wong proposed interpreted the X boson as dark matter particles since it is neutral, not baryon, and can be composited particle of large mass astrophysical object. In this particle, it is proposed to take manifestation of these particles in spectra of cosmic rays of ultra high energy, energy of order 10 in degree 11 GeV. By this formula, can reproduce the experimental data from ultra high energy cosmic ray. The parameters J and T was obtained from spectra cosmic rays proportional to E in degree -3. This is a spectrum of ultra high energy cosmic rays. Experimental points from this work and solid curve 1 from this work for the dark photon. Solid curve 2 is our spectrum of photons from the X17 boson in contrast with formula 8 curve without taking account the boson X17. The solid curve 3 correspond to mass 1 GeV. Curve 4 correspond to mass 10 GeV. Dashed curve 5 correspond
Alexander,
to mass
Alexander, do you hear me? You have 1 minute more.
Thus me convinced that one more confirmation of the existence of X17 and X38 boson with masses of 17 MeV and 38 MeV has been obtained in light of experimental data from cosmic rays for ultra high energy that are not achieved with modern accelerators. Heavy particles of large mass also do not contradict this experimental data. This is reference. Thank you very much for your attention.
Thank you very much. Any question? No question. Thank you very much again. Thank you. Is Dr. Chaudhuri from India, probably also online presentation, yes? Yes. Okay. Do you hear us? Dr. Chaudhuri. He is. Okay. No. Okay. In this case, next, the Giorgi. The Giorgi is here or not?
Yes, I'm here. I'm online.
Okay, please share your screen.
Yes, absolutely.
You have 20 minutes in total. It means
Yes.
16 minutes for talk and 4 minutes for questions.
Perfect. Then I put
Okay.
my
Please
clock
share your screen.
Yes. You can see, right?
Yes, but not full screen mode.
Yeah. Okay, perfect. Now it should be fine. Is it?
Okay, great. Go ahead.
Okay, so hi to everyone. Thank you for having me here today. Today I would like to tell you something about our relatively recent work involving low-scale seesaw solution to the MW and the G-2 anomaly, a work realized in collaboration with Luca Merlo and Stefan Pokorski. So let me start first with a very quick overview. I'll try to be as short as possible. We know that the standard model presents many problems and puzzles. And as model builders and theorists, we should ask ourselves whether we can solve these problems and puzzles individually in disconnected sectors, or whether we need something that captures more of them at once. But of course, it's already hard taking one type of new physics at a time. Like, there are many possibilities. Putting more of them is even harder. Virtually infinite possibilities are there. So what I would like to work on and focus are those combinations that actually mutually enhance each other, and there are not many of them. So I will give you a concrete example of such a type of unique models later on, but bear with me for a moment with this type of introduction. So I would like first to focus on one of the standard model problems that follow the title of the talk, that is low-scale seesaw solution, so neutrino masses. We know that neutrino have masses, order of magnitude should be over 0.01 electron volt. We don't know yet the ordering, so we have measured lots of quantities, and this is really amazing. But the important thing is that neutrino have masses, and the standard model cannot predict it. Why? Because the way fermions in the standard model gets a mass via the Higgs mechanism need left and right chirality for each of the fermions, and we don't have right-handed neutrino in the standard model. So there are many ways to give neutrino masses, but I think we can kind of agree that the simplest possibility is simply to follow what the other fermion do in the standard model, that is, we add a right-handed partner. Now, the question, though, nevertheless remains, that is, why their mass is so small. We are all talking about 0.1 electron volt, is like a millionth with respect to the mass of the electron, that is the lightest fermion we know of, excluding neutrinos. And in this sense, we enter in the family of models which are called seesaw mechanism models, type 1, type 2, and so on and so forth. What is the main idea? The idea, let's look at this method, so the standard model effective field theory, and let's try to find a higher dimensional operator that can generate neutrino mass. And we are very lucky because there is already a dimension find a single operator that generates neutrino mass when the Higgs takes a value. And you can see already that as this 5-dimensional operator must be suppressed by new physics scale, that if this scale is very large, we're naturally suppressing the neutrino mass. Now, this is an effective description, but it can be concretized very easily. For instance, we take our right-handed neutrino that I will call during the talk sterile neutrino, heavy neutral lepton. For me, there will be all synonyms. We write the Yukawa couplings as for the other fermions. We add an extra term that this is completely new, that is a Majorana mass term, because this right-handed neutrino is sterile under any singlet, under all standard model symmetries, gauge symmetries. So we can allow it and introduce a new scale that is completely free. Now, if I diagonalize the mass matrix, I found the famous seesaw relation, which basically is the model-dependent realization of the argument I gave on the effective field theory. What is the downside of this is that if we want Yukawas for the 1, it means that the scale of new physics should be very large, for the at least 10 to the 10, 10 to the 13 GeV, and so on, which is very hard to test. And of course, people thought about and invented a new class of seesaw mechanisms, which are called low-scale seesaw mechanisms. And the idea here is not to have a large scale, rather a very robust symmetry that is protecting the smallness of the neutrino mass. So let's take an example. Here I have 2 right-handed neutrino, N and S, and we impose as a global symmetry the lepton number. So we write all terms that respect lepton number, but we allow for small breakings of the symmetry. So we want the symmetry to be very robust, but not exact. And if we do the same exercise, we write the mass matrix and we compute the neutrino mass, you will find that the neutrino mass is proportional to the breaking parameters of the symmetry.
which basically means, as I said, that this robustness of the symmetry that is making neutrino masses that small. And this is true at all orders in loops, so this is protected, and it's a very elegant solution, which of course should embed it then in a larger class of theory. Now, this is, as you saw from the title, very essential in our discussion, but I would like to go a little bit after this. So already with heavy neutral lepton, these right-hand neutrinos, we have introduced new physics, and it's very interesting. We have many variations that we can do. But the question remains, like, what kind of extra piece we could add that makes a difference? And of course, the question is very broad, depends a lot on what we believe is true and what is not, what is a puzzle, what is a problem. But on this, in this talk, I would like to focus on anomalies, and I would like to use them as a motivation to explore some of the models that are possible, and to look for these specific and interesting, unique models that we can create. So I will consider two anomalies. The first one is the G-2 of the muon, which this is very nicely was updated last week or the week before, which basically updated the result and found this 5 sigma discrepancy. And the mass of the W boson by the CDF collaboration, which is reporting a 7 sigma discrepancy with respect to the standard model prediction. Now, what I'm saying is very nice and so on and so forth. But of course, I would like to say that we have to be careful, and because these are somewhat controversial, both of them. The G-2 on one side show this 5 sigma prediction, the deviation with respect to the prediction of the standard model of 2020, the white paper, which is using E plus E minus from the standard model hadronic vacuum polarization contribution from the cross section of E plus E minus. While if you consider the latest results from lattice, this tension actually changes and reduces a lot to order of 2 sigma or a little bit more. So, okay, it's not still standard model, but it's much less, is much more compatible. And the same goes for MW. Here, the situation is a bit different, but the latest measurement by Atlas that came out some months ago is their most precise to date and is still compatible with the standard modeling, compatible with CDF2. So it's not clear exactly why they keep finding different measurements, and of course it needs further investigation. But bear with me for this presentation. Let's assume that we can use these anomalies to explore a bit models of new physics, and we'll use this as input for the model. So now let's enter finally in a bit, what am I talking about when I say unique model and so on and so forth. So let's consider the sterile neutrinos. We have them. What can we do with them? Well, of course, we introduced them to explain neutrino mass, so we can do that. Then also only sterile neutrinos can in principle explain the MW anomaly, so this is fine. But we cannot use them to explain the G-2. And the reason is that if you want a deviation, the G-2 for the 10 to the -9, that is what has been measured, we need mixing angle parameters, this theta mu n, that should be of order 1. And this is in strong tension with the current experiment at collider. So we cannot explain really the G-2, so we need something more. Now, among all the possible extension that we can add, this is the one that we propose, that is, we introduce beside these 2 sterile neutrinos, also one vector like lepton, which is a doublet under SU2, or the psi L and psi R. Now, this really shows a unique property that I will explain very soon. So let's go through these 3 observables one at a time. Regarding the mass of the neutrino, the situation is basically identical to what I explained with the low-scale seesaw mechanism. So we simply consider the exact same Lagrangian as shown, but we have to add the new interactions coming from this new particle psi. These do not really play an effect in generating the neutrino mass, so we find exactly the same formula that can be achieved really easily with taking, for instance, our mass scale lambda at order of TeV. We can now look to something new. So MW, how does sterile neutrino affect it? Well, in the standard model, mass of the W is computed from 3 input parameters, the most precise measured ones, that are the G Fermi constant, alpha electromagnetic, and the mass of the Z boson. Which means that if we have new physics that starts affecting these input parameters, we are somewhat indirectly modifying also the prediction for the mass of the W boson. And in this case, as the muon decay from which the G Fermi is extracted is producing neutrinos, of course, the introduction of sterile neutrinos in the theory basically has non-unitary effects that diminishes this interaction in the vertex, and has an impact of MW. I don't want to put here precise number because I doubt anyone will remember that. You can find a precise number in the paper, but the idea is that if you have a particle at order TV and Yukawas of order, let's say 0.1, you can easily accommodate that. So we're not introducing any particular tuning here or hierarchy. So they're pretty natural. So this can be achieved with neutrinos. We now go to the more interesting part, from which my initial claim really is about. Of the G-2, what is it about is computing the correction to this dimension 5 left-right operator. The fact that it's left-right is really important because in the standard model, contribution to such operator must always be proportional to the Yukawas. And the reason being that we need to do a flipping of the chirality of our lepton, so the only object that we have is a Yukawa, so we are suppressing light particles with an extra powers of the mass. And this is what makes contribution to the G-2 generically small. They say chirally suppressed, unless you introduce some new type of new physics that can unlock something new, that is a chirally enhanced contribution, meaning that we put this new particle into the loop, but we don't need anymore to use the Yukawa, for instance, of the mu, which is very small. So it's true that we had new physics, which suppress the amplitude, but we don't use the Yukawa of the muon. So we are kind of have a game here that enhance the process. Now, the diagram that I circle is the one that really has the leading contribution. And now if we want to estimate it, here I put two diagrams in the flavor basis, so you can see roughly how you would do it directly from the Lagrangian. And now let's estimate the contribution of these two loops. You will say, okay, there's a product of 3 Yukawas, a loop factor. 1 power of mu comes from the definition of the G-2, so that you cannot remove. And then you would look at the leading order term, which is suppressed by 2 powers of the masses of my new fermions. And now, if you want to obtain something of order 10 to the minus 9, you just plug in the numbers. And you would find that the mass of these particles must be of order 10 TeV. When I say order, I mean it could be 20, 30, like I'm not putting an exact number, but just to give you an idea. And this, of course, would be bad because you would need to take larger Yukawa for the mass of the W, and that's really dangerous for unitarity and so on. You would need also find harder to test this type of model at collider. So you see, this would make the model really not appealing at all. So you may wonder, why are you telling me something about this? And here is the, as far as I know, unique feature of the model. That is, if you compute explicitly this contribution, is exactly 0. So it cancels accidentally the leading chirally enhanced contribution, and we're left with the next leading order. Now, this was pointed out some time ago by Arkaniamed and Harigaya as a violation of the criteria of Wilsonian naturalness, and was further studied afterwards precisely
Excuse me, Arturo, you have
Yes.
5 minutes more for your talk.
Perfect. Basically, thank you. And we further studied from the last point of view that is going to mass base and so on, but it's really a unique feature, as I know, as far as I know, of accidental cancellation that has really a huge impact in phenomenology, because with this next leader order contribution, we can keep our heavy fermions to the scale of order 1 TeV. So this is what I was meaning at the beginning. Now I would like to add a very small detail, that is the same diagrams that generate the G-2 by simply removing the external leg of the photon will also generate a radiative contribution to the mass of the muon. And this is very interesting because if you look at the mass of the muon, this doesn't have this accidental cancellation. And this means that so you have somewhat a mismatch in powers of the heavy mass for 2 different observables, which allow for a very interesting game in a chart, for instance, seesaw. So if we want to generate fermion masses via loop. This was not really treated in our discussion, but it still is a very intriguing possibility to consider this type of model for. So let me get to my final plot, the so-called Monet plot of this presentation, and then I will quickly summarize. In this plot, you see in the x-axis the mass of the doublet, and the y-axis the mass basically of the heavy neutral leptons. The contours are the ratio of the one loop correction to the muon mass with respect to the experimental one. And I would like to stress that all this parameter space is allowed. So don't be fooled by the colors, which can be misleading. This is all allowed. The colors means different things. That is, in the gray area, one of the Yukawas must be larger than 1. So we start approaching the grayish area of non-perturbativity and so on. So one has to be careful there. The red and green colors basically refers to the ratio of the one loop correction to the muon with respect to the tree-level quantity in the Lagrangian, which of course means that if we start with a tree-level contribution, we would like the radiative correction to be rather small, not to spoil it. But if, for instance, if you wanted to impose some symmetry and generate everything radiatively as in a charge seesaw, you would actually prefer to go into the red region instead of the green one. So this is up to you. But what I would like to stress is that thanks to this unique feature of the model, we have basically predicted that we need these particles to be with a mass that is smaller than 1 TeV or something similar. You see, depending then on which area you want to be. And this, of course, is very important because it makes the model much more testable, even a collider presenting this feature, which is not available for other models. So given this, I would like to go to my summary. I hope I was not too quick, but I should be on time. So in this model, we introduced basically 2 heavy neutral leptons and a vector-like electroweak doublet, which allow for possible simultaneous explanation of the mass of the neutrino, the mass of the W, and uniquely the G-2 of the muon with a physics of order of 1 TeV or even lower, which of course allows for a very rich phenomenology interplay accessible at collider. And who knows, something more. This is something that we are trying to explore, but of course this is accidental, so you don't really know which type of observables will be influenced by this type of cancellation, and we don't know if there are many more models that present such a feature in observables that maybe we haven't explored yet. So this is something really exciting and stimulating for someone doing pheno. I thank you very much for your attention, even though I cannot see you, but I hope it was nice. And if you have any questions, I'm here.
Oh, okay,
Please.
thank you very much. Thank you very much. Thank you very much for timing also. So we have time for questions. Online questions? No online questions? If there are no more questions, let us thank speaker again.
Thank you.
Thank you. And the last speaker of the session is Dr. Panda from India, I suppose.
Thank you so much. Thank you so much. Okay. So should I start? Yeah. Okay. So thank you so much for giving me the chance to talk here. Okay. So good afternoon, good night. I don't know, whatever in each and every country in the world. So, okay. So let's start our talk today. So this is the outline of my talk, and now I'm just going to start about the particle content. So like whatever I will talk right now, that will be a talk based on the model and which we have made for explaining neutrino phenomenology, and then electron and muon G-2 leptogenesis, and then testing of the model. So coming to the first one, that is particle content. So in that particle content, you can see that the model is nothing but the extension of a standard model, which is called as BSM, beyond the standard model. And in the BSM, we have just taken 2 extra gauge symmetries like E1 B minus L and E1 L minus L mu. So here I have given the particles in the table. Here like in the extra of SM particles, we have taken the NRI and SLI, where I represents 1, 2, 3, and then similarly that SU3C, SU2L, and U1Y quantum charges for these extra particles are like 110, 110 because they are singlet under this symmetry. But they has a non-zero value of quantum numbers in the new U1 gauge symmetries, which is U1 B minus L and U1 L minus L mu. You can see that for U1 B minus L, NRI is -1 and SLI is 0. Similarly, for U1 L minus L mu, I mean NRI and SLI has the value 1, -1, and 0 respectively. So as the extra particle of I mean beyond the standard model, we have also taken 2 singlet scalars, which is chi1 and chi2. They are singlet under SM, but they have the non-zero values of U1 B minus L and U1 L minus L mu, as you can see from the table. Now you can see that in a very layout language, I can tell that whatever the extra gauge symmetries are there, that means U1 L minus L mu and U1 B minus L, these 2 should come to the U1 EM, that means the electromagnetic gauge symmetry at the very last. So how it is coming, I have just taken a picture of that, like at the very first the SM as well as E1 B minus L and E1 Le minus L mu were there, and then after the chi1 breaking, the symmetry breaking through chi1, we can have SM as well as E1 Le minus L mu, and after that there will be again symmetry breaking through chi2, and after that we can have the SM gauge symmetry. From the SM gauge symmetry we can have the SU3C cross SU2L cross E1 EM through Higgs mechanism. So can you please go next? Yeah, so this is the Lagrangian, this is the Lagrangian of the model, whatever we have considered here. So in that Lagrangian, you can see that the L SM lepton is the nothing but the standard model Lagrangian, and after that we have taken extra particles. So coming from that extra particles, there are some extra terms in the Lagrangian which are given in this expression SM plus something. So in that something, you can see that there are three big third bracket. So in the first third bracket, it is nothing but the Dirac mass for the neutrinos. That right-handed neutrino. It is the Dirac mass of the active light neutrinos, and the second one is the nothing but the mixing between SLI and NRI, and the third bracket is nothing but the mixing between SLI and SLI. So coming to the next one, please. Yeah, so from these Lagrangians we can have the mass matrices like MD, MNS and MU. As I have told that the first bracket was showing the Dirac mass, the second bracket was nothing but the mixing between N and S, and the third one is MU. So just from this Lagrangian, whatever it is showing in the upper panel, from that Lagrangian we can have MD, MNS and MU expression. So yeah, then next. Yeah, so as we have already made our Lagrangian and particle contents as well as the mass matrices, then we can go for the numerical analysis calculation. So coming to the numerical analysis, so coming to the numerical analysis calculation, you can have that there is a table. In the table we have a plot. We have mentioned all the Yukawa couplings like YDE, YD mu, YD tau, then YN1, YN2, YN3, whatever we have mentioned in the Lagrangian itself. So these are all the Yukawa couplings as well as the V1, V2 are there. V1, V2 is nothing but the waves for the two singlet scalars, that is chi1 and chi2, and then phi1, phi2 are the phase angles. So if I just put these values in such a range so that our neutrino phenomenology will be satisfied, then the table will be like that, like YDE, YD mu, YD tau will be of the order of 10 to the -6, -3, -2 and like that, and YN1, YN2, YN3 we have taken as of the order of 1, you can say, because it is like 1 to 2, 0.1 to 2, that means it is of the order of 1. And now for the Y13 we have taken as the order of 10 to the -7 and like that. So just next. So next. Yeah, so with the help of these values of the numerical aspects, numerical parameters, we can have a condition that is like mu. Like if I just put all the Yukawa couplings values in that mass matrices, then we can have a condition like mu is very, very less than MD, which is less than MNS. So this condition is nothing but the inverse seesaw condition. So that's why we can have an inverse seesaw flavor in our neutrino mass generation. So the active neutrino mass matrix mu can be found from that expression which is given in equation number 1. You can see that this is nothing but the expression for the inverse seesaw condition for the neutrino mass generation. So next. Yeah, so now we have just given the neutrino phenomenology results here. This is the sum of the results I have just put it here. So here what we have shown, there are 4 panels I have shown here. The first panel is nothing but the mass of the neutrino with respect to sin square theta 1, 3, and then second one is the correlation between sin square theta 1, 2 and sin square theta 2, 3, and the third one is again the correlation between sin square theta 2, 3 and sin square theta 1, 3, and the fourth one is delta CP versus sin square theta 1, 3. From this figure you can see that like from the first panel I can tell, I can conclude one thing, that a summation of mi, which is the mass of the active summation of the mass of the active neutrinos, these are very constant from our model. right? It has a very small range of values, like let's say 0. If I just see it carefully, then we can have a conclusion that from our model we can constrain the summation of mi is like 0.0592, 0.061 or 0.062, like that ev. And from the second and third panel we can see that sin square theta 23. From the figure you can see that from the sin square theta 23 value, it is basically allowed the octant, I mean upper octant, because the all the ranges are like 0.5 to 0.6, in between 0.5 to 0.6. That means it is basically allowing us to have the upper octant, because our upper octant means the theta 23 value will be greater than 45 degree. And from the fourth panel you can have a conclusion that delta Cp has a very constant value. It is of the order like up to 140 degree or something to 240 degree or something. This is a very constant value for the delta Cp. So from this case also we can have a very constant value of the delta Cp, which is coming throughout our model. Then next. Yeah, now coming to the testing of the model. Next. Yeah. So this is a very important to know that whatever we have taken as our model, is it correct or not? Like obviously we have to test, we have to probe the model in the near future as well as the current experiments. Otherwise we can't say that our model is correct or not. So for that case, I have just taken 3 future long baseline experiments like DUNE, T2HK, T2HKK. I think all of you have heard about these experiments very well. So I don't want to spend so much time on these experiments and I mean what are these and what is this. So I'm just going directly to the result. So in that result you can see that I have plotted here DUNE, T2HK and T2HKK. So here what I have plotted, like I have just plotted the theta 23 versus delta Cp value where both are true. Now here like the model, I mean the values of the theta 23 and delta Cp, whatever coming from our model, these values we have taken as a test value, and we have taken the true value as the new fit value, new fit 5.2. So these are the true values we have taken, and the test value we have testing these values of the models so that we can have these plots. So in that plot you can see that I have just plotted here 2 sigma and 3 sigma of model fit, as well as DUNE 3 sigma and 5 sigma of the experiment. So here from the figure we can see that the DUNE has a very big parameter space for the 2 sigma as well as 3 sigma of model fit, but T2HK has a very small range of allowed parameter space for 2 sigma and 3 sigma model fit. Similarly, T2HKK has a very large, I mean very big parameter space, allowed parameter space for 2 sigma and 3 sigma model fit, obviously compared to the T2HK. So as a whole, we can have one conclusion from that result, which is given in the next slide. Can you please go to the next slide? Yeah, so from these models, whatever we have plotted in the previous slide, the results can be coming as like 2 sigma and 3 sigma allowed regions of proposed model are compatible with 5 sigma parameter space of DUNE. That is for DUNE result. Then what is for T2HK? For T2HK, we can conclude that 3 sigma allowed region of model can be tested by 5 sigma allowed region of T2HK. And also, can you please go back? No, go back. Yeah. So here in that T2HK plot, if you see very closely, then there is a small blue, yeah, I think blue, yes, small blue circle is there inside of the just there is very near to a star, there is a small circle of blue. So this is nothing but a exclusion of the 2 sigma region from that point, from that parameter space. Then come to the next slide. I will just tell that. Yeah. So I have written here a small contour of parameter space which is excluded by 2 sigma confidence level of the model is very much compatible with 3 sigma allowed range of T2HK. Thus, if this type of region is present in T2HK with the experiment, then our model can exclude, I mean our model can be excluded by 2 sigma confidence level with the help of T2HK 5 sigma confidence level. And for the T2HK HKK, similarly, we can have 2 sigma allowed region is testable by 3 sigma allowed parameter space of T2HKK, and 3 sigma allowed region of model can be proved by 5 sigma confidence level of T2HKK. Now, next slide. Yeah, so now we will talk about, first of all, I have made a model and I was just doing the numerical for phenomenology as well as the numerical calculation for that model. Then I used to test that one with the help of Dion, T2HK and T2HKK. Then what I will do, I will just search for the model. I mean, I will search something which can also be expressed, which can also be successfully explained by the model. So that is nothing but the electron and muon G minus 2. So for the electron G minus 2, there is a magnetic moment, anomalous magnetic moment for electron is present. So the value of the anomalous magnetic moment of electron is nothing but 48 plus minus 13 to 10 to the power minus 14. It's a very small amount, but still it is a non-zero value. So we have to see that how this extra delta AE is coming from. So if I take a BSM, that means from that BSM some contribution will come to the Lagrangian of the delta AE value. So this is the Lagrangian, that G B minus L E bar gamma mu E Z B minus L mu plus Z E mu E bar gamma mu E Z E mu mu. So this extra Lagrangian is coming from our BSM model, so that it will explain the electron G minus 2 problem. Now this is the expression for the delta AE, whatever I have written here, where X is nothing but the Feynman parameter. Now next slide. Yeah, so this is the Feynman diagram, whatever I have plotted here. This is nothing but L means like electron and gamma is coming out, and then ZB minus L is 3. I mean the ZB minus L as well as Z E mu. These two gauge bosons are responsible for the extra electron G minus 2 value. So next slide. Yeah. So for the muon G minus 2, similarly, we have two values like FNL and as well as BNL, but I can apologize that I did not include here the recent values of muon G minus 2. This is the older value of muon G minus 2 result, whatever it is written here. But recently in this month only there is a new result coming out. So I did not add that one. Okay, now coming to the next slide. So we have to explain that one also, that what is the value, I mean, how we can explain the delta A mu value. So this is the expression for delta A mu, where X is Feynman diagram, a Feynman parameter again. And these are the Feynman diagrams for muon G minus 2, where L will be A mu for that case. Now coming to the next slide. So in that slide, we have just plotted here electron and muon G minus 2 calculations. So you can see that from the first panel, we can have a delta AE versus MZ E mu. So in that case, the grid lines is nothing but the delta AE experimental 3 sigma allowed region. And for the second panel, delta A mu versus MZ E mu. And in the third panel, we can have G versus M. That means the coupling versus mass plot. So from all of the three panels, you can see that our model can successfully explain electron and muon G minus 2 simultaneously. And in the last panel, you can see that not only our model is giving exact value of electron and muon G minus 2, it is also giving the allowed parameter space which are already mentioned for the current, from the current experiments like CCFR, CLO, coherent LAR, and all these things. Okay, next slide.
Do you hear me? You have 2 minutes more.
Okay, fine. Thank you. Next slide, please. Yeah. So I have a very last point coming from our model, which is nothing but collider mount. Then coming to the next one. Collider. Next slide. Yeah. So in that collider analysis is nothing but the experimental procedure to search new heavy gauge bosons. So in our model, we have seen that our among these two extra symmetries, B minus E1 B minus L, from the E1 B minus L, the gauge motion is coming as Z B minus L. That Z B minus L is of the order of TeV. So we want to see the collider experimental bound on B minus 2 values, the mass of the Z B minus L. So that's why we have taken, searched the colliders experiments, and then we got some results, what I have written in the next slide. Can you please go to the next? Yeah. So in that next slide, you can see that collider searches we have plotted. So what is in the y-axis? Y-axis means the sigma b. Sigma b is nothing but the cross section into branching ratio, and the x-axis is mass of the ZB minus L in GeV. Then you can see that the experiment, that means collider experiment, is basically, I mean, we are just taking the ATLAS experiment data. So ATLAS root S equals to 13 TeV data is giving in the red dotted line, and we our model, from our model, whatever the result is coming, it is showing in the black and magenta and blue color. So you can see that for different values of G, we can have a different parameter space, but most of the parameter space are allowed by the experiment. Okay, then next slide, please. Oh, then it is conclusion. Yeah. So in the conclusion, I can conclude my talk with some remarks that proposed model, whatever we have proposed here as a extension of standard model of E1 B minus L as well as E1 L minus L mu, this is able to explain small non-zero mass of neutrino, and it can be tested in future long baseline experiments like DUNE, T2HK, T2HKK with 5 sigma confidence level. Now, electron and muon G minus 2 has been already explained by the model simultaneously, and the acceptability of the model increases by the results with collider search. And also we have tested the leptogenesis, the baryogenesis through leptogenesis, but I did not discuss that one here due to time constraint. So I can tell all these things that, that leptogenesis, muon G minus 2, electron G minus 2, collider search, as well as that mass of the neutrino and the testability, all the things can be done in one model only, whatever we have taken as E1 B minus L and E1 L minus L mu extension of standard model. So I think the next slide is thank you. Yeah, thank you.
Thank you very much. We have time for a few questions.
Yeah, sure.
Please.
I have a short questions on the slide 18.
Yes.
Can you see the remarks, please? Please so. But one of the aim of the collider analysis is to find the heavy gauge boson. Why the new heavy gauge boson? It's maybe dark photon or not?
Yeah, so in our model, what we have taken, I told you that we have taken 2 extra gauge bosons, E1 B minus L and E1 L minus L mu, right? So these 2 extra gauge symmetries we have taken. From these extra gauge symmetries, we got 2 gauge bosons. Among these 2 gauge bosons, one is heavy, that means of the order of GeV, and one is lighter. Lighter means like it is of the order of MEV. So it can be dark matter, but a dark photon, but it will not be dark photon in our model, as we have taken ZB minus L as a gauge boson, which will be responsible for the neutrino phenomenology and that collider search cases, and ZE mu is responsible for electron and muon G minus 2. So in our case, it is not a gauge photon, but yeah, it can be a dark photon. Yeah.
Thank you. Thank you very much. Together we overcame all problems, technical problems. Thank you very much.
Yeah.
I would like to thank all people in the audience for their patience. Thank you very much.
Thank you so much.